This is the first part of the unit on the structures of simple solids, and we will be working through this relatively new material for you. You would not have seen it before. What are we going to look at? Well, there's 4 aspects to the structures of solids that we will be tackling. The first one is the description of structures of solids themselves. Then we're going to look at structures of metals and alloys. We will look at the structures of ionic solids. And finally, we'll do a bit of electronic structure of the solid materials. So what happens when things become solids? Let's take a look at solidification and crystallization. Generally, we have some kind of interaction between molecules that hold them together. So if we had to look at this molecule, for example, and we were to look at how that molecule fits itself into a crystal or a solid material, you're going to find that it will pack itself in a certain way. It can be in the orientation that you see over here, or it'll be in this orientation. We need to have a look at the actual structure itself and decide whether it's going to, what kind of packing is going to exist, what kind of arrangement of these molecules is going to be there. Is it going to be amorphous, which means no real shape, which is non-crystalline basically? Or what else are we going to expect? Is if we're going to have some kind of order between the molecules, such that you see something like this, where there's a regular order and there's a regular pattern. You can see that this molecule here repeats itself again and again. So that's some kind of order that's present. And so we're going to refer to those as crystalline materials because there's ordered arrangement of atoms in the solid phase. Okay, so to describe this repetitive pattern, we need to define what's called a unit cell. Okay, so what is a unit cell? Well, unit cell are building blocks to make up the entire solid. So if we had to look at these 2 pictures that we see on the left-hand side of the slide, the top one is a picture of amethyst quartz, and the bottom one is a picture of bricks that have been arranged in some kind of random order. Okay. What we need to look at is what are the possible arrangements of the atoms inside those materials that is going to give a regular repeating order of atoms. So if we had to have a look at what you see on the screen at the moment, you can see that a possible unit cell is where we encompass the green atoms. So we've got, well, green spheres. Let's not call them atoms. They are green spheres and orange spheres or red spheres, depending on what color you see. Okay, so a possible unit cell would be to look at this sphere, this sphere, this sphere, and this sphere. Okay, is that a regular repeating pattern in the unit cell? There's another simpler one, okay, where we do not have any of the red ones that are between 2 atoms. So if we had to look at this one here and this one here, you'll see there's a red sphere in between here, a red sphere here, a red sphere here, and a red sphere here. But in this arrangement here, you will notice that we've picked the smallest possible unit of the green spheres here, here, and here, with only one red sphere in the center. That is what we would call a preferred unit cell because it uses the least number of components. All right, and then obviously in diagram C, that's not a unit cell because the components that we're interested in are different. Okay, we can't link a unit cell when the components are different. So in such a unit cell, for example, this would be a different molecule, and this would be a different molecule. In order for us to have consistency in a unit cell, all the molecules need to be of the same type. Okay, so that's how we look at unit cells. Now, there are different ways to represent unit cells. We have 7 crystal systems. They are called primitive crystal systems. There are also 7 non-primitive, but we're not going to worry too much about that right now. What I want to explain to you is how are these determined? Well, they're determined by a technique called X-ray diffraction, and it's used to determine the unit cell. Like I said, there are 7 of them, and we're going to focus most of our attention on cubic cells. Okay, but you need to know what these 7 are. Okay, so you have cubic cells. Essentially, a cubic cell has all sides equal and all angles are 90 degrees. Then you get a tetragonal unit cell where 2 of the sides are of equal length and 1 side is of a different length, and all of the angles are 90 degrees. And then you get something called orthorhombic, where all 3 sides of the shape are different. So this side, and let me just draw it. This side, and this side are all different. So this would be A, B, and C. They're all different lengths, but the angles are all 90 degrees. Then we come to the situation where we get different angles, different lengths of the sides and different angles. So what you would see for monoclinic is the sides of the shape are all different, and one of the angles is set to 90 degrees. The other 2 angles are not 90 degrees. We get the triclinic shape, where all angles are different and all side lengths are different. We get rhombohedral or trigonal and hexagonal, where the conditions are given as such. So in this slide, you will see the 7 crystal systems and the considerations that we're going to take. As I've said to you already, these just describe the system in this column here. Then the relationship between what we call lattice parameters. Okay, so a unit cell is sometimes called a crystal lattice, especially if we're looking at ionic solids. We'll have a look at that in a moment. Okay, and then we see some other information here where the unit cell, how it's defined. Okay, and then some essential symmetries. Now, we haven't done symmetry just yet, but when we get to it, this particular section of the table will make way more sense to you. Okay. All right, so if we were to look at how to describe unit cells, if I was to give you some drawings with dots or anything in them, I would ask you to pick a primitive unit cell. Remember, a primitive unit cell is a unit cell that you can draw where it is the smallest number of possibilities of joining the dots together, basically. So in other words, in this case here, that I've highlighted, we should be able to find atoms or even molecules that will exist on those 4 corners that have been joined together. In this particular case over here, we have a non-primitive unit cell because we have one of the lattice points that is inside the lattice that we have chosen. It is possible to do this, but it's not a primitive unit cell. Okay, so in the case of the 7 primitive crystal systems, we have 1 lattice point within the unit cell, and with the 7 non-primitive crystal systems, we have more than 1 lattice point within the unit cell. There are 14 possibilities for the unit cells. These are called Bravais lattices. You need to just remember these words. This is new terminology for you. Of course, if I gave you some examples and asked you what would, let's classify this as number 1, this is number 2, and this is number 3, you'd be able to tell me immediately which one is primitive and which ones are non-primitive. Okay, so clearly number 1 is a non-primitive unit cell because there is more than one lattice point within the unit cell. Number 2 is primitive because it looks similar to the one that I've drawn over here. Okay, and then number 3 is also non-primitive because it has more than one lattice point within the unit cell.